and we will see some multimodal tasks that are linked also to your parcours, and some examples of model before a short conclusion. And we will have a practical work after. So let's begin with the introduction with two definitions that we will study during this lesson, which are multimodal machine learning and multimodal artificial intelligence. So these are two different fields, we can say. Multimodal artificial intelligence is bigger. It's englobe multimodal machine learning, which is the study of computer algorithms that learn and improve through the use and experience of data from multiple modalities. So it's when you have an algorithm and you pass, for example, images and text, etc. And multimodal artificial intelligence is more vague. It studies a computer agent able to demonstrate intelligence capability, understanding, reasoning, and planning through multimodal experience and data. So this is more it's closer to what is a human, because we can interact with the world with different modalities that we have: vision, touch, etc. So these are four senses: vision, language, touch, acoustic, so audio, that we can think of when we speak about multiple modalities. In AI, we study mostly vision and language, so text and images, but we can have audio, videos, etc. We can also ask ourselves, why do we need multimodal data? So when we just learn a model with images, as you have seen before, or only with text with NLP, you have a limited world model, a limited knowledge about the world. But when you add some images, text, so description of images or things, videos, sound, you have a better representation of the world, and so you are more robust if one of the modalities is noisy, for example. So this is a short schema, a short figure to show that with just images, you have limited output. But when you add multiple different modalities, you can think of different models such as autonomous driving, image generation, robot navigation, etc. For example, DALI is a multimodal system because you give some text and you receive image as an output. So yes, some example in medicine, some large example, where you can have some X-ray images and some text associated to these images, and you can learn to predict what is the link between text and X-ray images. You can have also a data set with images, question and answer, to have to train model to answer some question that you have. You give an image to the model, ask a question about it, and the model will respond to you with, for example, this type of response, of answer. And finally, you have even more complex multimodal medical AI with MedPalm done by Google that can take a lot of different modalities, so a lot of different images. And you can, it's a bit like ChatGPT, but specialized for medicine, and that can take images as input. And you can dialogue with the system to find some disease, etc. So first, let's see some recall about different architectures that are important for each modality. So the basic one, MLP, multi-layer perceptron, that is used a lot for vectors. So you can flatten images or just have an input vector and your output a class or something, a regression, etc. So this is the most simple model. You can have CNN for images because they can capture what is around the point of interest. So some spatial information around this point with some convolution blocks. That is divided in convolution, batch norm, ReLU, and max pool. So this is just a detail. And you have so RNN, recurrent neural networks, that are a bit harder to understand. So this type of network can treat sequential data, such as video, text, etc. And they have a memory. So here, for example, you encode the what inside a latent space. And after you encode the word time. And the memory keep information about the previous word what, but also keep information about the current word time. And it will do it for each word. Each time you will have a part of your memory dedicated to the previous one, so that you have a context of the sentence. And at the end, you can do some classification task or other things, or text generation, for example. You have different type of RNN, one-to-one, one-to-many, many-to-one. For example, if you have a sentence and you want to classify the sentence, if it's a good sentence, bad sentence, etc. This, for example, this one mostly for text generation, you pass I, it predicts the next word will go here, up, and predict the next word at each time step. So these are some details. But what is mostly used nowadays in multimodal AI is transformers. That's why, for example, is ChatGPT made of, or DALL-E? Not DALL-E. DALL-E is just a unit. So for transformers, we have some encoders and decoders. Encoders encode, for example, your sentence. So you have a very nice animation to understand what is the transformers on this website here. And you pass these encoded sentences, encoded words, to a decoder that will sequentially, for example, here translates your "je suis étudiant" to "I am a student." For each time step, it generates I. Then from I, it will predict am, etc., etc. And you stack these encoders and decoders to have a more powerful model to encode and generate more complex sentences. You can do the same with images. Here you can divide an image into different patches, for example, 6 patches, and you pass these patches to the transformers that will encode the image to do some classification tasks, for example. A bit more recall about the different steps to train a model, where you have the training phase, the validation, and the test. So during the training, you perform an epoch so you pass all your data sequentially, you predict the output, you do your gradient descent to optimize your weights, your parameter of the model. And when you have seen the whole training data set, you have performed an epoch, you pass to the validation part. Is someone asking question? When you have performed all your training and validation step, you can pass to the last one, the evaluation one on your test data set. So this is when you want to train the whole model, but something that is done and used a lot in multimodal AI is to use pre-trained model. So here you have a model, for example, a convolutional model that you want to classify something, images. You have your different convolution blocks, and at the end you have your MLP. You can train your model on a specific data set, a big one, and then you fuse the parameters of your model. And for example, you took only the convolution blocks and you retrain this last part to perform another prediction. For example, here you can have some natural images and you want to fine tune to have a better model on medical images. As here in this example, you can see some ImageNet. So ImageNet is a database of natural images. You train your model to perform some classification. And after that, you freeze the convolutional layer and you pass some other images of medicine images, for example, and you retrain your MLP layers to predict the good output of classification. Here it's tumors, I think, normal, benign, etc. So you are not You don't have to retrain the whole model at each time. You can use a lot of pre-trained models that exist on internet, so that you can play with them to perform your task. So, yeah, before it was easy because we have only one type of modality, only images, only text, videos, sound, etc. But now we have data set with, for example, 3 different types of images, images and text, video and sound and text, etc. So you have to treat all these different data. And you can have data that are close to what we call raw modality, close to the sensor. So photo, images, for example, are close to the sensor. A bit further, you can have language or detected object. For example, here is another modality. You have segmented the images into different parts, trees, people, horses, etc. And even further, with abstract modality that are far from the sensor, because here you have segmented the images, but also put a label on each part, cyclist, bicycle, sky, etc. So this is very far from the sensor, but these are 3 different modalities, for example. And here are some examples of multimodal case, where you can have an images and 5 captions, so 5 short text description. This is a multimodal data, 5 text caption and an image. This is also a multimodal data because you have your image and your segmented image with the segmented plane. And this is also a possibility for a multimodal dataset to have the 3 modalities at the same time, images, segmented images, and text. You can do whatever you want, add as many modalities as you want in a multimodal case. So to train your model from multiple modality, you have already existing data set online to pre-train your model and then, for example, fine-tune it on a data that you have for a special case. The most common data set are COCO for common object in context, where you have a lot of images segmentation, and some sentences that describe the images, 5 or 6 short sentences for each image. So this is a very common data set. You have Lion, so a bigger one with 400 million images or 5 billion images and text pairs. So here you have more complex description of your images. And you have a lot of different specialized versions. For Lion, you have Lion specialized for medicine, I think, for some part of plane, trees, etc. So Lion is a very big and very common data set to pre-train a model before fine-tuning it on other data set, smaller one. And for audio, you have audio set, which is very known with a lot of annotated YouTube video and a lot of hours of video to train your model with audio and video. So here the 2 modalities are audio and video because you have the sound linked to the video. So these are 3 common data sets to have already a lot of data to train your model, but you can create your own multimodal data set. For example, you can use a pre-trained model that can describe some images. So you pass an image to a pre-trained model, it will generate a sentence. And at the end, if you have a lot of images, you will pass off all your images of your data set, and you will have an image and a text data set at the end, so that you can train your model on 2 modalities, even if you have only one. So this is how to generate, for example, a multimodal data set for a small amount of data. So now let's pass to how we can train a model with different modalities. So a good idea is to concatenate the different modalities. For example, here we have RGB images, so red, green, blue. And if you have a depth measure of your images, you can concatenate it because it's very close, it's the same size, etc. So you can concatenate this 4 channel to your model and predict something at the end. But this can be done only if the 2 modalities are very close. Here, there are 2 images, so it's very simple. But otherwise, what is mostly done is encoding some modality into latent space. So here you have 2 different modalities, circle and triangle. So for example, images and text. You encode them in a latent space with MLP, CNN, etc. And then you can concatenate the 2 vectors and with the MLP learn a task on it, etc. So this is way more simpler to do because concatenate image and text is not really possible for multimodal AI model. So you will first encode into latent representation. And instead of concatenating the 2 vectors obtained, you can fuse them. So fusion can be very simple, a simple addition of the 2 vectors, multiplication, or using MLP that takes as input the concatenation of the 2 to generate a new one that is a combination of the 2. So to train this model, you can use different losses to encode them and to have some close representation. The loss is called the contrastive loss. So to explain, here if you have an image of a plane and the word a plane, you want the 2 latent space to be very close to each other. So at this point here, for example, but when you have an image of a tree and the word plane, you don't want them to be close because it's 2 very different concepts. So you will put, for example, plane here as before. Here, but the images should be very far from your encoded text. And this contrastive loss will force that to encode close concept close in the latent space and far concept far in this latent space. This allows you, for example, to create some captioning model. So a captioning model will take as input an image and generate a sentence that describes the image. And to train this model, you will encode image and text, do some alignment loss, so use the contrastive loss to align the different concepts, and train also a text decoder, and add a reconstruction loss here, so that during the test time, so when you use the model, you just pass your image, and because these 2 latent spaces are very close, you can directly decode from your image latent space, and you obtain some text. So this is very small, but when you use this contrastive loss to align the different concepts, you can do some geometry in this latent space. So for example, you can use some text and so add some sound, and you can obtain, you end up in a new point in the latent space. And when you decode, you can obtain an image that is a combination of your text and your sound. You can do the same here to obtain some videos, or encode videos and sound and obtain the text, etc. So you can do a lot of geometry in this space that allows you to have some creative AI model to generate text or videos or images. So this is a first good step to train your model to encode and to align the representation, but train, for example, a CNN for images and a text for recurrent neural networks is hard because it's a lot of parameters to train. You have to process a lot of data. And CNN. So you choose on internet the best one that can encode images or text. You force the weights and you just keep the latent representation, and then train your MLP to do the alignment for you. And so you have only few parameters to train, and it's way more easy if you have not a lot of data. It's very practice, and it's what is done mostly currently in the state of the art. So this is when you have two different specialized model. But what is mostly done nowadays is using transformers. So you have an image and a text. You encode your image with VIT, so an image transformer. You have your encoded images, and you concatenate your text and your images, and you pass this to large language model. So large language model is, for example, ChatGPT, Llama, etc. Some big language model that can generate some text. So here, for example, it will be some image captioning. You pass an image, and it will generate some text with ChatGPT or the large language model. So here is an example of existing model where they have a vision encoder here, a language model that is frozen. So they just train this vision encoder to align the representation of the text and the image, such that the language model decoder can understand what is the image and decode the description of the image. Also, for aligning your representation, you don't necessarily have to train even an MLP, because you have existing very good model that are called foundation model that already align some modalities for you. So here is an example with Clip, which is trained to encode image and text and to align the representation of each. So you have text as input and images, and it will align the concept of dog with some dog images, etc. So train on mostly natural images. Here it's also a model that has to be taken to be frozen later. And after that, you can do some retrieval task or generate some sentences, etc. So here is an example of what you can do with Clip. If you pass a text sentence to Clip, and you have a set of images, but you don't know which images is related to this caption, you encode your caption, you encode each one of your image, and then you find the nearest neighbor between your latent space, so your latent text, and your latent images, so that you can extract the closest images in this latent space to have the good images caption relation. For foundation model, so we can call also foundation model a large language model. So BERT, GPT, T5, PALM, all these things are also called foundation model. They are LLM, but because we use them pre-trained and don't change the weights, we can say that they are foundation model used to generate some text or some steps to reason for reasoning in the world, etc., to perform some action in robotics, for example. So LLM are very, very used in a multimodal AI to generate sentences. So now let's pass to multimodal task. Some example. So the most common one is image captioning. So it's when you have an image and you want a description of your image. So it's the link between computer vision and NLP. And here is an example. You have your image of a dog. You have your captioning model that will generate this sentence: the happy dog is standing in the ocean. And so to train captioning model, need some images and some text that describe the images. So here are some examples of data that you need to train your model. And during training, you will pass your images and your text to the model. It will encode, etc., and then generate an image, not an image, a sentence, and you will compare this sentence with so this sentence, which is generated with the ground truth. And when the two sentences are too different, you will penalize your model. And when they are close, you will say, okay, it's good, continue. And at influence time, so when you use the model in everyday life, you cut this part of text and just encode images. And then you just choose the sentences that are generated from your model. So here are some architecture to show you that you can use CNN and so LSTM are sort of RNN, so complex RNN, to encode your image into a latent space and then decode from this latent space some text to describe the image. These are some examples of what can be done in a medical use case with X-ray. So you have some ground truth associated to each image, and the model learns to reproduce the ground truth. By learning that, you will learn some knowledge, some link between some part of the text and some part of the images, make some relation, and after, it will generalize to unseen images. If he saw some pattern in the image that are linked to a tumor, etc., it will say, okay, we can see a tumor here, for example, etc. So these are things that can be done in medicine, and it is done through transformers, not with this type of model with CNN and STM, mostly with transformers. You have an encoder, you pass your images, and then you have a transformers decoder, you pass your text and your images, and it will decode and generate the next part of the sentence. So here, for example, you have just the beginning of the sentence, and it will generate the next word and do a loop like this. Another common task is VQA, so visual question answering, which is also at the bordering between NLP and computer vision. So here it's close to image captioning, but now you have as input an image and a question, and you want your model to answer to the specific question and not only to describe the image. So to train this model, you need a text composed of a question and an answer, and some images that are linked to the question. So to train your model, it's quite simple. You pass the image and the text, you predict the answer, and you compare with the ground truth that you have in your data set and during inference time, so everyday life using of the model. You just generate a bunch of answers that you need to perform your task. Again, some example of old architecture with a specialized module. So here you can see some image part to encode the image. Here some text part to encode the text with RNN, CNN, and you end up with two different latent vectors that you are combining with MLP, multi-layer perceptron, to a unique representation. So this is the multimodal fusion part that we have seen at the beginning. And then you perform your task to answer the question. So here, because it's only a count task, you just need a MLP. But if you want to generate a more complex sentence, you will use some RNN at the end, for example. But you have mainly three different parts: image, text, fusion, and then the generation of your answer. Some example in medicine where you have a different data set and challenge. VQA Med is one that happens, I think, every year. They generate some new data set. with images, very different images, question and answer. And people have to create the best model that will answer the question according to the image. So I don't know a lot in this type of images, but you can see some example. And the way it is done, mostly, the best models are mostly image encoders, for example, CNN or transformers that are frozen. Also, large language model like ChatGPT. You first encode the image with the frozen transformers or CNN. Then you pass the latent representation to the MLP, and you concatenate the representation of your MLP with the representation of the text of the text, so your question, and you pass this to the large language model, and it will output some answer. So, for example, ChatGPT will do it very well if you encode properly in a way that it understands the translation of the images to text, to a sort of text, a Latin vector close to the one of your question. And you have also a multimodal conversational system. So this is a bit like ChatGPT, but last version when it can take some images as input. So you pass images, it can describe the image, you can have a conversation with drawing, etc. So these are this type of model. This is an example of what can be done. You pass an image, you want the system to answer to your question, and also to retrieve other images, for example, of the same bird, etc. The way it is done, it's again with a large language model, because they are very good to generate text and to understand the translation of the images to a latent vector that is close to the one here. So this is just the training process, not very important, and a very good model here to describe the encoded image part that is encoded before passing to the large language model. And here are some examples of what can be done. So you have some instructions. Here the guy or the girl will just ask some question about what the model can see in this type of images. Is this dangerous, etc. What is the disease, etc. And this is closer to MedPal that we have seen at the beginning, where you can discuss with the model while passing some images. It's a bit like an assistant. It will give some hint of the disease that the patient has, etc. And a new part, so less linked to medicine, but a part that came a lot the last year is vision and language navigation. So here it's more in robotic, where you, so it's too small, but you have some task to perform for the robot and some question, and it will from the task and the question, it will perform some action and answer you. So here at each time step, it will register the current image, and from this image, predict an action to perform until it can answer the question and resolve the task. And the way it is done, it is mostly with, again, transformers. You have images, an instruction, you pass this to a planner. Usually the planner is a large language model, and it will output some steps to perform the action with respect to your current state. The current state is represented by the image, so what the robot sees. And then the controller so will just tell to the motor of the robot what is the link between catch the can and, for example, grab it, so action the arm like this. It will just translate this to motor action, basically. So now some examples of models. So you have this funny model where you can do what they call any-to-any generation. So you can, from a text, generate images as usual, but you can also generate some videos with sound or only sound, etc. You have a lot of different possibilities. And this is done with mostly transformers. And you learn to a common representation space, so could be a sort of big space where same concept are close and far concept are far, but this time with very big transformers and a generative model like DALI. And so it is able to translate from one modality to another, basically. You have Coca, which is also very famous to do some contrast, some captioning. So it learns also to align the representation, but at the same time to describe the images it sees. Because when you just align the representation, you tend to lose a lot of information that is not in common between image and text, for example. But with this model, because it decodes the textual information, the model should keep all the information, even if it's not relevant, so that you maximize the amount of information inside your small here piece, so your latent space. So this is a model useful when you have to align some representation, for example. Another one, because Copa do some alignment, but only between text and images. Here is a bigger one, ImageBind, where you can align some images, videos, text, audio, depth images, EMU, so action, egocentric videos. And it learned to align all these elements together. So it's a bit like Coca, but with 1, 2, 3, 4, 5, 6, 7 modalities. So it can be very useful if you have non-usual modalities to align, so different modalities as images and video, images and text. Sorry. You can, with ImageBind, you can perform some good thing like image retrieval. So you pass image and text to ImageBind, and you will end up with two different vectors. And because the ImageBind learn to keep same concept close and far concept far, you can perform some geometry. And this is what is done here, where you have images and sound, and it will not really generate, but retrieve images that are linked to this concept in the images and the concept in the sound. So people and clapping will end up in a wedding. A clock and a church bell will end up in a church bell mostly, for example. So you can perform some geometry in this space. This shows that the model can understand some concepts that are relevant for here this task. And you can also do some segmentation, but this time not with text, but with sound. So if you have a dog which is barking or sea waves, the model will say, okay, the dog barking is this part of the image or video, and sea waves come from this part here because the paddle here is moving forward. Keyboard, the same for these images with a keyboard typing and clock alarm. Here. Another cool model, which is a bit used in medicine, is Blip2. So it's a conversational agent which can take as input images, for example. And it is used because, so here is a bit some detail. You have your image, you encode it, and here you have a bit complex transformers, we can say. So this image encoder and large language model are frozen, and you just try to align and keep information, relevant information with these transformers here. And it is used because in medicine you have some tuto or something on Kaggle that can be found here, I think. Yes. So where they just fine-tune this model. to take as input images, so medicine images, and a question, and to output an answer. So here you have, if you want more detail on this, you have a tutorial to reproduce the training. But at the end, their model is capable to do some visual question answering. So after, because they retrain the model, but here typically, here we can see the question, the predicted answer, the actual one in the data set, and the image linked to this question. And so they are able to retrieve some good answer with this fine-tuned model. So here, they use a pre-trained BIP2 to perform this task. So that you just have to have a small data set to retrain it. It's not necessary to have a billion or million of images. Just for 1,000 of them is enough. And so not lastly, but one important thing is made Palm, so made by Google. So Palm is a large language model. It's a large language model of Google, which is behind the Gemini, for example. So a big one, and made because it has been fine-tuned on medicine data with images and to produce some answer to some question. And the way it is done, here you have your image encoder, and it's not because it's Google, they don't say perfectly what they are doing here, but they have some adapter, some translation to pass from the image to some to make a link between image and medical information. So they put some expert knowledge in this model, and then they translate it to text such that the LLM can, the large language model here, Palm can answer the question, generate some text linked to the images, for example. And for the last part, for the robotic part, you have a very famous one, which is called inner monologue, where the model is able to make some planning for the robot. So it takes as input images, the current state, and the human sentence. Can you bring me the drink from the table? And it will perform some planning until it reach the final state to bring the coke to the human. And the way it is done, so the human pass some sentence to the model, and the model will say, okay, the robot first have to go to the table, then go to the table will be passed again to the large language model, and it will have some feedback from the scene. The scene will tell him, I see a Coke and lime soda. And so the large language model, thanks to this free information here, will say, okay, what kind of drink would you like? And then it will discuss a bit with the user before continue to pick the Coke, for example. So here is the architecture, but not very important. And yes, just a short demonstration of that is able to. So to solve a simple task, but quite impressive. It's the current state of the art in robotics, for example. And this is done again with time, as before with the medicine part. Here, time has been used, T is for embodied, has been used to embodied agent, here robot. So time is very used by people because it's a powerful large language model. So it can just here Palm predict the different steps to perform. So just so as a conclusion for this part before passing to practical work. So you have different specialized architecture for each one of your modality. So CNN for images, LSTM, RNN for text. Video, you have LSTM and CNN both together. For vector, you have MLP that are used. But nowadays, what is mostly used is transformers and pre-trained models such as LLM or BLIP, for example, that are very used because you don't have to retrain the whole model. It's the most important thing. You just pick some pre-trained model on internet and use them for your personal case. A good thing to do is to align some representation between the two modalities. So here you encode your two different modalities into latent space so that they are closer, and then you do some alignment between different concepts so that you can perform some geometry in this space, or you can keep some good knowledge about each concept. And here, as a resume, three different good data sets, Coco, Lion, audio set. If you don't have a good pre-trained data set, you can still train personal model on one of these data sets to have a first pre-trained model for you. And so, yes, as I say, nowadays we don't use a lot RNN or CNN. We use mostly transformers that can directly handle multiple modalities at the same time. You just pass images, text, videos, audio to the transformers, and it will output whatever you want. And a good practice is to use some foundation model so that you keep the knowledge that they acquired during the training to your personal task. And so this is the end of, so not a lot of information to keep in mind, just the practical part will be more useful when you will learn to play a bit with different type of model and how to search on a famous library. Here, there was just some hint how to use them and how they work. But for yourself, you will mostly rely on this part here, hanging face. Yeah. And si vous voulez, on peut prendre une pause de 10 minutes. Ça laisse une heure, 45 minutes si. Mais parce que là, le TP va pas être dur, mais il va être long parce qu'il va falloir charger les modèles qui sont un peu gros. Donc c'est pour ça que le cours a été divisé en une heure plutôt qu'une heure et demie 30. Euh, voilà. Donc on peut prendre 10 minutes de pause si vous voulez. Um, So let's take a bit more time to pass to the practical work. So first, all the models that we will use here are available online. Yes, on this library thing, Hugging Face. It's here that you will find all the models that you need to use. So big model with 7 billion parameters, so big LLM, and also visual transformers, etc. All these models are open source. For example, Mistral, the French LLM. And so you can find them on Hugging Face, which is the most common library that we will first have to install because it is not installed on Google Drive, on Google on Colab. Ouais. It's that also libraries. Can take times. Um, so the first model that we will use is a clip with an example of, I think, image retrieval that I took when it will happen. Okay, so let's take the next drivers. So to import a model from Hugging Face, first you have to pip install transformers. This will install you the library. And then to import your model, you just have to type from transformers import, and here the name of the model you want to use. So if we type them here, you can see some different model. I think the first one that we use is this one. But you have all the code, etc. available, and the usual library, NumPy for matrix, PIL for images, matplotlib to plot images. So here the model is download. I hope this images still work, and we will load a bunch of images that are available online. So 1, 2, 3, 4 different images. An image of a cat, an image of a dog, image of a plane, an image of a dog and a cat. And here I just create text, some text that are linked to the images, a photo of a cat, a photo of a dog, and a photo of a plane. So these are 3 different categories that I want to have. And I put this into processor. So processor is just so that the model import from Hugging Face understand all the data, the images, the text, etc. So you have some parameters, but I will not enter into details. create some text and add some images. The images are this one here, these 4 images. And here, let's display the image of a dog and a cat. So you have a dog and a cat on the screen. And we will encode these 4 images and see which one is the closest to each concept. So image of a cat is one concept, image of a dog is another one, and image of a plane is the third one. And we will see the distance between each concept and each image. So here we pass the data to the model. So model is just, I define it here, it's clip model that I define here. And processor is to pass the data to the model. And inputs are the data, so the text and the image. I'll just play the cell. It will take a bit some time to process those images. And after that, so here the process is done, and I can retrieve, so plot some probability that I obtain with the third line here. And I plot some probability so that the image of a cat is linked with almost probability 1 to the cat concept. Image of a dog here is linked to the dog concept, plane to the plane concept, but interestingly, we can see that image cat and dog is not linked to one concept, cat or dog. It's a bit of both, a bit more cat and a bit less dog, but there is a confusion here by the model, but it's normal because there are 2 animals, cat and dog, in the image, so it cannot classify the image in one category. So this is to show you the clip geometry a bit, the distance, to illustrate the distance between each concept, so that you can retrieve some images or perform some geometry in this space. So this is the first simple model that is often used to encode images because it has very good encoders already aligning some concept. So now, okay. So now let's continue to the next model. This one is built. Yeah. And you will perform some VQA task. So the first thing again is to import the model from the transformers library. So this one is very small compared to clip, so it will be quicker normally. And here you have 2 different cells, depending on which one you want to use. Here there is a pre-existing image that I will use, but if you have some images that you want to play with, you can upload your images to your Google Drive with this specific cell and put it to the model. So here, for the moment, the images that I use and I found on the internet is this one, 2 cats on a sofa with some remote. And the text here is the input is an image and a text because it's a VQA, so visual question answering. And the question is, what are the cats doing? And again, importantly, to pass all the inputs to the model, you have to call processor put the image, the text, and some parameters again. And after that, you perform a forward pass, and you can see that the model predicts sleeping, is predicting sleeping. So this is a good answer. And you can play with different images if you want, if you import some images. It's not a big model, so it will not have a good answer all the time, but you can play with it and have some funny answers sometimes. Are you able to run the different cells? Because sometimes the model are big, so it can crash the process. Ah, prendre le temps. Vous avez bien Internet? Vous avez réussi à faire tourner le premier déjà ou même pas?
C'est sur le premier.
Ok.
Mais là, c'est pas sur le normalement.
Ah.
Tout à l'heure, je sais pas.
Parce que ah oui, c'est ça.
Ouais.
Ah oui, ok. Ah, c'est le télécharge des trucs. Vous êtes sur Internet et du oral, ok. Oui, le truc de la fac. Ouais.
C'est dangereux. Sur ma table. C'est pas le même. Mais il fait. Qu'est-ce que tu veux dire? Continuez sur.
Okay. So just let's pass to the next one to just take a look and not necessarily play all the cells. So the form model is a clip seg. It uses a clip like the first one, and have a special decoders to perform some segmentation, so to divide images into different parts. And so here again, to import the model, so from transformers, you have your model here that is on Hugging Face. Ah, je sais pas. Attends. Ah, c'est pas le bon, c'est le bon. Ah, yes, this one. So here you have different clip segmentation models. And just as before, if you want to import images, play this cell. Otherwise, if you want to use pre-existing images on internet, I choose again this one to divide the images, this image. And I want my model to divide the image in 4 different parts: a cat, a blanket, a remote, and sofa. So I create 4 text vector of text of size 4, and again pass it to the processor's function. And with this, so with torch node add here, it's to specify to the model to not perform the learning step, so the gradient descent. And you just pass the input here to your model that you have import earlier, and get the output at the end. So it will take a bit of time, yes. And here, the next step is just to show you how the model divided not the caption, the image. So you can see the 2 cats here, the blanket, the remote here. So the model missed this remote because it's partially blocked by the cat. The cat is on top of the remote, so it didn't catch the second remote. And the sofa. So the model put a higher probability on sofa on this part because we can directly see the sofa, but he put some low probability here because he is not sure if it is a blanket here or a sofa, a bit of both. So he's not quite sure. But you can see that even this model is not very big, and it can already perform some good segmentation. So again, if you want to try on one of your data, you can put your images here and replace, of course, XXX. And if you want to try another images, and so this is a segmentation. So again, a multimodal model because it takes as input four different text, a vector of text and an image, and return a segmented image. And the last one, so I'm not sure if it will work directly. Let's see. And yes, so the last one is a small diffusion model. So a diffusion model is like DALI, where you have your prompt, you are encoding your prompt with some model, obtain a small latent space, and then decode it. So now this is you encode your prompt, you have a diffusion model here, you decode, you obtain a small image, and you have a model to upscale your image to have some DALI-like images. So this model is called a Stable Diffusion XL, SDXL, but it's a bit big. So it will take time to download. Here. Oui, il y a un endroit où il y a deux, faut pas lancer toutes les cases à tout le temps.
Ça, c'est pour une fois, moi, c'est sur l'ordinateur, mais c'est possible de télécharger. Oui, c'est seulement.
Et ensuite, il y a ouais, ce type de cellule-là, il faut l'exécuter que si vous avez l'image à passer. Alors, est-ce qu'il a fini? And so yes, the last model is a diffusion model. So the input is only a text string, an astronaut riding a green horse, and again passing. So here he will do the diffusion process. 50 steps. And here, because it's a diffusion model a bit bigger than the previous one, we don't just call the model, there is a whole pipe to enroll it. And you just have to call the pipe with your prompt to give to the model. And after, you will obtain an image. And so an astronaut riding a green horse. So here the model catch because when the model is too small, it can mess up between what is green. Sometimes the astronaut is green and the sky is green, etc. Here we can see that it catch all the thing quite good. The horse is green and it's the astronaut is riding the horse, but still you have some details like here and also here. Some details that are not very good, but it's a small diffusion model. But you can play with it, enter different prompts here, and it will generate other images as at your demand. So these are the four models that I showed you. And if you want to go further for the evaluation, for example, with this practical work, you can test the model of the thing. You can use this different model with other data. And you can try to find the best image with a stable diffusion, for example, with respect to the prompt thanks to clip. So this could be an idea. You generate a sentence, so you give a sentence to the stable diffusion model, you generate the image, and then you pass the image and your prompt, so your text to clip to see if the two representations are close or not. And for example, while it is not close enough, you generate again and again images to have the perfect final images. This could be an idea to do. And you could also generate images with so this stable diffusion, while the condition in the prompt is not satisfied using Vilt. So Vilt is Vilt was this one for VQA. So for example, here you could say pass the images to the model and ask the question, is the horse green? And if it is yes, you stop. But if it is no, again, you generate another images until the horse is green. For example, this could be a small project to be done for this evaluation. So just some hints, some ideas to go further, but you can do whatever you want. Find other data, other model on Hugging Face to use, for example, and implement them on Colab. I don't ask you to train something because you cannot train those model on Colab. Even fine tune them, it can be hard on your own data set. You can try, but can take some time. So just use them as they are on the plugin face, import, create or use the data set, and do some interaction between the different models, and you will have a nice project. So yes, this is the idea. And it concludes the practical work. So the practical work was very simple because in multimodal AI, you can't train a big model directly on Google Colab. So we just use pre-train one, and it was to show you the power of even small model that you can find online. Et voilà.
Je mets une image complètement différente à chaque fois, même si on met le même texte.
Ouais. Si je relance, ça va prendre un peu de temps. Là, ça génère. Là, ça génère. Donc là, je crée le prompt. Donc le texte a passé au modèle. Et là, j'appelle le modèle avec ma phrase. Là, c'est en train de générer. Et en dessous, c'est juste pour visualiser. Ouais. Et à chaque fois, ça va être une image différente. Si vous voulez avoir tout le temps la même image, il doit y avoir un moyen en fixant, avec certains paramètres, en fixant l'aléatoire.
Est-ce qu'il est capable de toujours prendre l'image, par exemple, il reprend l'image qui va me faire, il va faire mieux, et ensuite, ça, mais en mieux, et à chaque fois, ça fait plus propre, genre, si je vais aller tout à l'heure.
Ouais, là, par exemple, on voit qu'il n'a pas du tout. Il y a plein de choses qui vont pas. Mais ce modèle, il va juste générer une image à partir d'un texte. S'il faut avoir une meilleure image, ouais, voilà, il faut utiliser d'autres modèles. Donc, comme ceux qui sont plus hauts, par exemple, passer l'image à un autre modèle qui va dire, en fonction de la question, ou en fonction, il va dire ça va pas, et ça va faire une boucle. Et, après, il y a des moyens d'avoir de plus belles images par exemple, en utilisant un modèle pour générer la phrase ici, au fur et à mesure, ajouter du détail pour capturer ce qui ne va pas, ajouter du détail dans la phrase par rapport à ce qu'elle n'est pas, régénérer, faire des boucles. C'est des choses qui peuvent être faites. J'ai arrêté le partage. Voilà. C'est bon en ligne aussi. Je peux suivre, il n'y a plus personne.
Oui.
Très bien. Je vais arrêter là. Le Zoom. Là.
Ouais.